So up until now, the whole focus of the class has been on taking a function and figuring out what its derivative is, and then possibly doing something, some application, for example, with it. In this last chapter, we're going to go the other way. The question I want to answer now is, if I give you a function, can you give me another function whose derivative is the original one? So in a sense, I'm almost trying to go backwards. Now, there's a name for this. The technical term for what we're looking for here is the antiderivative, which we're going to represent with a capital letter F. So cap f of x is an antiderivative of f if and only if f prime of x equals f of x. In other words, cap f is the derivative of f of x. Okay, so let's look at an example. See if we can figure out the antiderivative of this thing. So what I'm looking for is a function whose derivative is x squared. Kind of a natural place to start is to say, well, look, I'm talking about a monomial here, right? X to a power. And we have that power rule that says, well, when I differentiate, the exponent goes down by 1. So to go backwards, it's natural to think, well, maybe the exponent just needs to go up by 1. So maybe my cap f of x is x cubed. Well, unfortunately, that doesn't quite work, because if we differentiate this, we get not x squared, but 3x squared. That's not quite what I wanted, right? That 3, that constant term out in front, is getting in the way. Okay, but I can adjust for that, right? If I put a 1/3 in front of my hypothetical antiderivative, does that work? Right? Did that fix the problem? Well, if I differentiate this, cap f prime is equal to 1/3 times 3 times x squared. And yeah, the 1/3 and the 3 cancel. They go away. Excellent. All that's left is x squared. That's the original function. This is looking good as an antiderivative. Now, if you're listening carefully there, notice I didn't say it's the antiderivative. I said it's an antiderivative. Because take a look at this function. 1/3 x cubed plus 1. The derivative of that is also x squared. Or for that matter, I could really put any number I want at the end. And I could add any constant, because the derivative of that constant is going to be 0, and we're going to end up back where we wanted to be with x squared. So my general answer to the question, what are the antiderivatives of x squared, would be 1/3 x to the third power plus any constant. And I really want you to get that plus c bit in your head, right? Because that's going to come up over and over and over again throughout our entire discussion of antiderivatives. Okay, so can we generalize what we just did? Can we come up with kind of a power rule for integrals similar to our power rule for derivatives? Well, yeah, we can do something very similar here. So first, remember, this is the example we just did. So I want you to kind of think through how we got from x squared to 1/3 x cubed plus a constant. First thing I did was I increased the exponent by 1. And the second thing I did was I multiplied that by 1 divided by that new exponent. Okay, I'm going to generalize this to get my answer here. The general antiderivative of x to the n is 1 over m plus 1 times x to the m plus 1 power plus a constant. Okay, I want you to hold on to that we're going to use that a lot, right? That's a formula you really need to internalize, just like hopefully you did with the power rule for derivatives. But I want you to hold on to that for just a second while we introduce a little new notation. Okay, so we're going to start off if cap f prime of x is equal to f of x. In other words, cap f is an antiderivative of little f. Then the way I'm going to write this is with that kind of, it should look to you like a stretched out I, right? Because the name for this is an integral. All right, so what I would say is the integral of f of x dx is equal to cap f of x plus c for any real number c. All right, so this is how we're going to write this. So with that in mind, let's revisit that power rule. Right, the way I would write this using my new notation, the integral of x to the n dx. That dx tells me the variable that I'm integrating with respect to. And that is important because we're integrating with respect to x, not the n. If we're integrating with respect to n, it would be a completely different thing. So the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus a constant. And we do have to throw in this little caveat. This does not work for n equals -1. Obviously, when n equals -1, that will make the denominator 0, and we'd be in all kinds of trouble. That x to the -1 is a special case, and seeing what the antiderivative of that is, that's going to have to wait until the second semester of the class. We'll talk about that some more then. All right, so let's take a look at an example. One of the nice things about that formula is, other than the not equal to -1 restriction, there weren't any others. So this works not only for integers, but for fractions as well. Right? So if I wanted to find, for example, the integral of the square root of x, dx, I could rewrite that as x to the 1/2. Okay, now my power rule applies. Right? This integral is equal to, see what I did? I increased the exponent by 1. So I went from 1/2 up to 1/2 plus 1. And I multiplied by 1 over 1/2 plus 1. There's a little arithmetic. 1/2 plus 1 is 3/2. And the constant bit there, that's 1 over 3/2, which is 2/3. And there's my antiderivative. And you can check these, right? You can check that pretty quickly. If you differentiate that, yeah, it does get back to the square root of x. Okay, so that's the basic idea. Right? Basic idea of what we mean by an antiderivative. In the next lecture, we're going to take a look at some more examples, see how we can kind of expand on this power rule a little bit, and we're going to add a couple of new integral properties that are very similar to some of the derivative properties that you've seen already.